So Copernicus actually then is credited with kind of beginning what we call the revolution to putting the sun back in the center of the planets orbit the sun. The Earth orbits the sun, the other planets orbit the sun. And this is again what Aristarchus said back in 260 BC, I think, or something like that. So right here, introduce you to Copernicus. So the thing about it, though, was Copernicus said, recognized that if we go ahead and make it a sun-centered model of our solar system, what we now call our solar system, we put the sun in the center and the planets orbit the sun, we know then that we can explain retrograde motion apparent retrograde motion of the planets. So he's like, that's cool. The thing, though, is he could not use his model to accurately predict where his model could not predict where the planets would be. Okay, in other words, he would predict where the planets would be and the planet wouldn't be there. Okay, and the problem was, and I'll go ahead and highlight it, was that he said that the shape of the orbits, of the planets, the Earth and the other planets as they orbit the sun actually is a circle, and that was actually the barrier that needed to be overcome. Okay, so but he is attributed with beginning the heliocentric or sun-centered model, the revolution towards that vein. So this actually is Tycho Brahe. Now, if you have your notes handy, you need to draw a line through this. Copernicus hired Tycho Brahe to make more precise measurements. That is not true. I will say that Tycho Brahe took on the Copernican revolution and gathered precise measurements to try to solidify this heliocentric model. But as somebody pointed out to me in the slide, you can tell it's not true, because actually Copernicus died in 1543 and Tycho Brahe was born in 1546. Okay, but I will say that Tycho Brahe came after Copernicus. Okay, so Tycho Brahe continued that vein. So this actually is Tycho Brahe's cool little lab, and I would imagine that's Tycho Brahe himself with his little assistant there. Now, he did not have a telescope, but he gathered some outstanding observations. This kind of looks like a little angle thingy. Okay, so he did not have a telescope, but he did observe this actually is a supernova. He called it a nova just because nova means new, but we now know that this is a supernova. He observed that, which actually, the fact that he saw a star explode and then go dim again, that proved that changes happen in the heavens. And so actually that was a barrier that people were trying to get over at that time. So Tycho Brahe observed those planets. He saw nova. Your textbook also said he saw comets, okay, which again, the heavens are changing. That's against the current thought of that day anyway. So here's the deal, though. Then you see the word Kepler here? Johann Kepler was the third person that I want to talk about. Okay, so Johann Kepler, actually, I think he was hired by Tycho Brahe, but I'm not sure. I know Kepler then went ahead and took Tycho Brahe's data. And the big thing Kepler did right off the bat was to basically change from the orbits needed to be circular to the orbits needed to be in a shape we call an ellipse. An ellipse is kind of like an oval. I'll show you a picture here in a minute. But that was Kepler's big change, that finally then he could go, the sun-centered model actually could predict where the planets would be if we go ahead and change from circular orbits to elliptical orbits for the planets. So I'm going to talk you through 3 laws that Kepler came up with. These laws are just specific to the motion of planets. Okay, so there's Kepler. The first law is going to describe the shape of the planets. It's an ellipse. The second law describes that actually planets, when they're closest to the sun, move faster And then when they're farther from the sun, they move slower. And the third law says individual planets, it depends on how close a planet is to the sun in its orbit. So for instance, Mercury has the closest orbit to the sun. It actually travels the fastest. Let's see, here's Neptune. Neptune has is the farthest away from the sun, so actually it travels slowest in its orbit. So those are kind of a summary of Kepler's 3 laws. So let's take them individually. So Kepler's first law is that the shape of the orbits of the planets is an ellipse, not a circle. So actually I would argue, and it wouldn't be too hard to make an argument, that an ellipse is, a circle, that you see here, is a type of an ellipse. Okay, what ellipses have are, this is an ellipse, what ellipsi have is actually 2 foci. Okay, there's 1 and there's 2. Okay, the foci, then actually the distance between the foci out to a point along the ellipse actually is the same. So you could actually go ahead and take a pencil and kind of draw around to make an ellipse like that. The thing about a circle is that it is an ellipse, but the 2 foci overlap. Okay, so foci overlap. Okay, so that's an ellipse. Now, ellipses can be kind of flatter or more circular. So here we have over here, we call that their eccentricity. It's a property of an ellipsis. The more circular an ellipse is, okay, it actually has an eccentricity value of 0 if it's a perfect circle. The more flattened out it gets, okay, the farther away the foci are, and it kind of gets flattened out. The eccentricity value of the flattest it can be is an eccentricity value of 1. So on to Kepler's first law. So like I said, Kepler's first law said that as the planets orbit the sun, they are actually orbiting in an ellipse. So you can kind of see the blue ellipse drawn around. But it gets even fancier. Remember, ellipses have 2 foci, and one of those foci is where the sun is. Okay, so that is actually the way the planets are in their orbit about the sun. The sun is at 1 foci, they're an ellipse. So actually we talked here earlier in this class that there's a time when all of the planets, including the Earth, is close to the sun. We call that perihelion. And there's a time when as the Earth orbits the sun, it is far from the sun. Now this is kind of exaggerated, but we call that aphelion. Okay, and the way I remember it is kind of like if you are going to parry, somebody with a sword, on guard, that sort of thing. You're kind of close, so that's close, and ap is far away. So all planets have a perihelion and an aphelion as they orbit the sun. The sun is offset at 1 foci. Put another way, if you're trying to kind of get a perspective on how this all works, we'll go ahead and call this Earth's orbit. Outside here is Mars' orbit, okay? And then actually, like we saw earlier in this course, a fair bit away is Jupiter's orbit. But can you see where they're all elliptical? The sun is at a common foci, and they all actually lie in what we call the plane of the ecliptic. Law looks like this. It basically says equal areas will be swept out in equal time. So I'll kind of show you what that means. Bottom line, like I try to explain it, is that at perihelion, when the planets are close to the sun, actually it's going to be going fastest in its orbit. At aphelion, the sun is going to be going slowest in its orbit. Okay, so with that in mind, let's go ahead and mark, I'll call this A and B, okay, and C and D. It's all about counterclockwise. Okay, so everything's going counterclockwise. So if we make segment A to B, okay, it's a certain amount of time, and that same amount of time is actually how long the planet takes to go from C to D. Okay, you can see actually it is going fast here, and it's going slow here, like that, okay? So then the equal areas come into this. Basically, if you take that stretch, it went in a certain amount of time. Okay, that, as I've kind of put in blue, is an area, and this is an area, and we'll call this A1 for this area, and we'll call this A2 for this area, and those areas are equal if the time it took from segment AB is the same time from C to D. Bottom line, it goes fastest at perihelion and slowest at aphelion. And this is one of the things I think is so cool. Actually, this is Kepler's second law, and it is consistent with what Newton would say about gravity influencing the orbital velocity of an object. I think that is so cool. So on to Kepler's third law, and it's maybe my least favorite because it's kind of summed up into this p squared, that's supposed to be p squared is equal to a cubed, okay, where p is actually the period. Period means time to kind of return to the same location. So these would be orbital periods of the planets. So here we have orbital periods of the planets in years. Notice how long it takes Pluto to complete one orbit, 200 almost 250 Earth years to complete one orbit about the sun. But my point is this. Oh, then A is, remember the ovals, well, I didn't emphasize it, but the long part of an oval actually is called the major axis. And if we take half of that, that's actually what we call the semi-major axis. So actually that distance for each of the planet's orbits are right here. So we do this a lot in science. We basically try to come up with what we call some correlation between period and, in this case, the semi-major axis, and AUs means astronomical units, the average distance between the Earth and the Sun. So if we cube this, if we square the period and cube the semi-major axis, actually this is what we come up with. Okay, and can you see where these are approximately equal? Bottom line, and actually I think here's a figure from your textbook that kind of reinforces this. The further the planet, so this is along the y-axis, along the x-axis, okay, we have distance of the planet from the sun. So notice that here we have the planet is farther from the sun, okay. Then notice that actually as it's farther from the sun, it has a slower orbital speed. Okay, so this is slower, and this is the farther away the planet is. So those are plotted. And then here, up here, this is actually plotting kind of a nice straight line correlation. That's what you like to see in science. If we go ahead and cube the average distance, and if we square the orbital period, this is what we get with regard to the planets.